Hi everybody, welcome to our first lecture on electricity. Now there are sort of two types of electricity. There is electrostatics, also known as static electricity, and electric current. And there are some similarities, of course, between the way both of those work, but also some things that are very different. So we're going to start off with the idea of electrostatics, also known as static electricity. Now to begin with, to understand about electricity. The study of static electricity itself goes back a long way, the ancient Greeks. Around 700 BCE, they noticed that when you rubbed amber with wool, it would actually attract very small bits of material. And they documented that. But it wasn't until later on, the discovery of the atom, the real understanding of what's going on with static electricity was understood. When the atom was discovered, it was discovered that it wasn't just one thing, it was made up of three particular particles. Now actually there are many subatomic particles, but there are three in general. The proton, the neutron, and the electron. Now in the structure of the atom, the protons and the neutrons are located in this region in the atom called the nucleus. Sort of central region of the atom. And then the electrons are somewhere out here. Now, for a long time, it was believed that all the particles were jumbled together. They call it the plum pudding model or something like that. Later on, a guy named Niels Bohr developed a model of the atom that looked a lot like a planetary system, with the nucleus like the sun at the center, and the electrons in very specific orbits, much like planets around that. But that was later further refined to understand that this region where the electrons exist is something called the electron cloud. And it's sort of done that way because the electrons aren't fixed like planets. They have the ability to move, not only within different levels of that cloud, but actually to the ability to leave that cloud in and of itself. Now, with the discovery of these particles was the discovery of some very specific properties of each one of these particles. These particles have what's called an electric charge, and there are two types of electric charge, positive and negative. Interestingly enough, those terms were invented by Ben Franklin. Play around a lot with electricity. You might remember the whole kite story, which, by the way, he's lucky he wasn't killed doing. So that's sort of the basic idea. Electrons have a negative charge, protons have a positive charge. Neutrons don't have any charge at all. But more specifically, these particles have very specific mass. The mass of a proton, 1.673 times 10 to the minus 27 kilograms, and the mass of a neutron, 1.675 times 10 to the minus 27 kilograms. Then the electron, 9.11 times 10 to the minus 31 kilograms. So you notice the electron is about 1,000 times smaller than the proton and a neutron, which is why something you learn in chemistry, that the atomic mass of anything, of an atom, is usually based on the number of protons and neutrons. Those make up the predominant amount of mass. But for our study here, one of the things that we're concerned about is the fact that not only do they have a charge, positive or negative, but there's actually a numerical value. So the symbol we use in electrostatics for electric charge is a lowercase q. And charge is measured in this unit, capital C, for the Coulomb, named after Charles Coulomb. We'll talk about him later. So a proton has a charge of 1.6 times 10 to the minus 19 coulombs. And you'll notice the electron has the exact same magnitude of charge, just that it's considered to be negative. Charge of a neutron is 0. Now, we've all kind of played the game probably of maybe rubbing our feet in socks like on a carpet that allows us to sort of sneak up on someone and then sort of zap them with an electrical shock. But how does that really work? How do we sort of cause that to happen? Well, if you think about it, the way life works is things tend to be electrically neutral. We're not always walking around zapping everybody, things like that. But somehow in that rubbing process, we change our electrical nature. And so to charge an object requires some sort of movement of electricity. Now, if you think about it, it's those electrons specifically that are able to move. You can't really move protons. That would change the element of what you have. But electrons are pretty free to move around because they're out there in that electron cloud. So any object that is negatively charged just means it has an excess of electrons, more than it normally would have. So anything that is positively charged is said to lack those electrons because it's the electrons that have the ability to sort of move around. But what's interesting is what happens when charges interact with each other. And there are a couple simple rules about charge interaction. Like charges will repel each other, and opposite or unlike charges will attract each other. In other words, if you have a positive and negative charge, they want to attract each other. If you have two positives, they'll repel. If you have two negatives, they will repel each other. Now, if you take that example, like I said, of rubbing your feet and your socks against the carpet, that causes you, for example, to become negatively charged, which means you took electrons from the carpet onto you, which automatically makes the carpet positively charged. But if you think about it, whatever electrons the carpet gave up, you must have gained. So turns out that charge obeys a specific conservation law. So when you rub objects together, one will lose and one will gain, but the amount lost equals the amount gained. In other words, you must conserve charge. The total charge of any system must always remain constant. Now, all of these ideas together produce a kind of neat trick, if you've ever done this. And that's taking a balloon, rubbing it on someone's head, and then giving it the ability to stick to the wall. Well, let's look at that in terms of simulation. Okay, so here we have our balloon. Here we have something to rub it against, and here we have the wall. Now, everything right now is electrically neutral, okay? And that means there is no excess or loss of electrons anywhere. We take the balloon, and we just do a little quick rub there. Okay, you'll notice that it gains a certain number of electrons. And at the same time, we see the positive charge over there on the sweater. And notice that the number of negatives and the number of positives are basically the same. They have to be the same because the electrons went onto the balloon, making it negatively charged. They left the sweater, making it positively charged. Now watch what happens when I let go of the balloon. Well, it immediately becomes attracted back to the sweater. And that's because they are oppositely charged. Okay, so that causes that. I'm going to rub them a little more. Okay, so we're building up a lot of charge on this balloon. Now, the other neat thing is I'm able to make it stick over here to the wall. But notice you're not seeing anything charge-wise on the wall. I didn't rub it against the wall or anything like that, and yet somehow it's able to stick. Well, how is that able to do it? Well, again, if we think about what was going on there, we'll use our friend's head here instead of the wall, instead of the sweater. So we've got our friend's head here, and we've got our balloon. Okay, both start off with electrically neutral. Okay, both have a charge of 0 coulombs, or they're essentially neutral. Now, when we brought them together, rub them together, just like in the simulation with the sweater, electrons came off of the sweater or your hair and onto the balloon. So now that when we separate the two, our friend's head is positively charged and our balloon is negatively charged. But now what happens to the wall? Well, let's consider the wall. The wall is neutral, which means if we consider positive and negative charge inside the wall, we're all equally balanced. But then we've got our very negative balloon. Now, if you think about that rule of charge interaction, like charges repel and opposite attract. So what happens is when the balloon is pressed against the wall with its negative charge, well, the negatives in the wall are repelled deeper into the wall, allowing the positive to come forward. And now we have opposite charges interacting, and that is enough to hold the balloon against the wall. Now, if you consider that force that's holding there must be really strong. Because if we were to consider the sort of free body diagram of that balloon, oh wow, free body diagrams, really? That's important? Well, if you thought about the forces, well, you've got the weight of the balloon. Now, the weight of the balloon itself is much larger than the charges that it's made up of. It's pressed against the wall, so that must mean there's a normal force here. Now, that's not in equilibrium. So it doesn't pop off the wall, which means there's some sort of force due to electricity, due to those positive and negative charges, that must be equal to that normal force. That keeps it from moving that way. What keeps it from moving down? It's a tricky question until you think about it. We have surfaces in contact and it would like to move down. Well, if we remember, the force that opposes motion between surfaces in contact is friction, and in this case static friction. And so the balloon is in equilibrium there. Now, let's sort of look at this again. Here we have our sweater, and it's showing it has a lot of positive and negative. In other words, it's neutral. The wall's all evened out here, positive and negative. The balloon is neutral. We come and start rubbing. This collects a whole bunch of electrons, making this negatively charged and the sweater positively charged. Again, if we let go, they attract because they're opposite. Now, watch as we approach the wall. Notice that the balloon is pushing, repelling those negative charges farther into the wall, leaving the positive to attract it. And again, that's what allows it to stick to the wall. So how do we charge things? Well, it turns out there are three ways to charge things. Charging by friction, charging by conduction, and charging by induction. Now, friction you saw there. Simply by rubbing things together, you're applying force. You're using energy, and that force and energy have the ability to kick electrons off of one object and onto another. And that's basically how you can charge something by friction. Induction and conduction are, in one case, one of them is pretty easy, I think. In the other case, it's a little more complicated. So we're going to look at conduction actually first. So to charge something by conduction, well, where friction, you can start off with two neutral objects and make them charged by rubbing together. Conduction and induction require that something is already charged. So for example, let's say I've got a negatively charged object and then I've got one that is neutral. Now, what happens is if I touch that negatively charged object to that neutral object, because there's so much charge on this object, it doesn't want to stay that way. So what happens is by making contact, charge will then flow directly from the charged object to the neutral object. And so that when I pull them away, they'll both be negatively charged. So now they both have a negative charge. So when you charge by conduction, you give a neutral object the same charge. In other words, if we start off with a positively charged object and I touch that, then negatives would flow off of that blue object and again make things both positively charged. So when you charge by conduction, you end up with the same charge on both objects. Okay? That's pretty simple. And in fact, when you sneak up and zap that friend of yours, you are a charged object. You're actually charging them for a moment by conduction, which is also why you kind of both feel a spark there. Induction's a little more involved, a little more complicated. Now again, you start off with something that is negatively charged, for example, and then something else that is neutral. And what happens if you bring it very close, but don't touch? Now what we saw, like with the wall, what that does is it causes, I like to use the term polarizes it. In other words, it kind of makes one side positive and one side negative. Now, while that occurs, if you then do what's called grounding one side of the object, well, what that does by sticking, for example, a wire here, it allows that charge that's on that one side a place to go. In other words, it wants to leave and go to the ground. And then you disconnect it from the ground, and what you have is still a negatively charged object. Now notice, it didn't lose any charge because you never touched it, you never made any contact. But now our other object is positively charged. Okay, so when you charge by induction, no contact, and you end up with the oppositely charged objects. With conduction, there is contact, and you get the same charge. Okay? So why do these work? Why does conduction and induction work the way it does? Well, the key is one of the key facets of nature. Charge will naturally flow from a high concentration to a low concentration. High to low, that's the way nature kind of works. Water naturally flows downhill from a high point to a low point. Heat goes from hot to cold, high temperature to low temperature. So electricity will go from where there's a lot of it to where there's very little. Now the least amount of electricity you can have is zero, neutral. So that's why when you conduct, it'll go from that high electrical charge into that neutral object. For induction, that's why we had to ground one side of it, because the ground is neutral and allows a place for that high concentrated side of the charge to actually flow down to a low point. The other thing that's going to be very, very important about static electricity is that static electricity can only flow on the surface of any particular object. It actually doesn't really penetrate through, which is going to be very different from current electricity that we'll talk about later on. It's also the key to a couple of things. Something called the Van de Graaff generator, which hopefully your physics teacher has an example of to show you, and in a way how lightning works. If your physics teacher has the Van de Graaff generator, it's basically this tall thing with a big metal ball at the top, and inside of it is a rubber band. And what happens is when you turn it on, electricity that is sort of coming from the wall is captured by the rubber band and then captured by the dome. Now what's interesting is all that electricity remains on the surface of the dome. And because they're all the same charge, they spread out throughout that dome. And the dome allows it to collect a certain amount of that electric charge. So now it becomes highly charged, and only on the surface of that. Now, let's say that you're getting close to that generator. Well, first of all, if you touch it, you're going to get zapped right away because you're neutral and it will conduct an electric charge onto you. But what's interesting is you don't actually have to completely touch it, because if you think about it, as you get closer and closer to it, what happens is this highly negatively charged starts to polarize you, and what it does is it induces positive charge on you, because you're standing on the ground and any negative charge is headed for the ground. And so what happens is when you get close enough, the charge will jump and create a spark, shocking you. Now, interesting enough, that's a similar way that lightning works. In lightning, up here in the clouds become charged. Now, there's still some debate on how the cloud actually becomes charged. Some people believe that it's due to ice particles falling through the cloud that charges it by friction. But somehow the cloud will become very, very negatively charged. Now, what that does, of course, to the ground, as it builds up stronger and stronger charge, it drives the negatives in the ground deeper and the positive towards the surface. Now, this is really what's fascinating what happens, is this opposite charges start to attract. And so the negative starts to sort of flow down towards the ground. And the positive kind of gets pulled towards it. And what happens is when they meet, that's when you get that lightning. But what a lot of people don't realize is lightning actually strikes from the ground up because the connection is made closer to the ground. That's also one of the reasons why they tell you never stand under a tree during lightning. And the reason why is because the tree provides a pathway for that positive charge to more easily get close to the sky. So it's most likely to get hit, and if you're standing next to it, you'll get struck too. Now, to show you the idea of how lightning works and the fact that it actually does strike from the ground up, let's watch this quick video clip of lightning acting in the slow motion. Now, that first part you see there is called a step leader. This is actually nearly invisible to our eye because it occurs so fast. That negative charge is descending in this kind of jagged step-like manner towards the ground, and it's spreading out in all directions trying to locate a good connecting point with the ground. Now watch, right about here you can see a couple of those step leaders are just about to hit the ground. Now watch there on the left. That's the point where it made a connection. Now notice that you saw that strike go upward. Okay, that's called the return stroke. Okay, and although it lasts for a very, very short split of time, you can see that it's discharging the cloud, and that's producing that segment of light. So clearly lightning can strike from the ground up, and that's where, of course, the electrical connection is actually being made. So where is it safe to actually be outside in case there's lightning? Well, never in the middle of the field, because if you're in the middle of the field, you're the tallest thing in the field, and you're very likely to get struck. But you may have heard that it's actually relatively safe to be in your car if it's struck by lightning. Now, what you may not know is the reason why, because I know what you're thinking, the rubber tires, that protects you. No, 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 no. The rubber tires do not protect you. You know what protects you? The fact the car is made of metal, and that property of static electricity. You see, if lightning were to strike your car, that metal frame, now remember, static electricity only flows on the surface of an object. So that static charge will simply stay on the surface of the car. It won't come inside. So it's the metal that's really protecting you. In fact, you could actually have the windows open and you could press your hand against the inside of the roof of the car and you wouldn't feel anything because it's only on the outside of the car. The rubber tires are actually a problem. It actually lifts you off the ground, and that makes it harder for the charge to get into the ground itself, possibly creating a charge on the car that could be dangerous. So if you're in a car that's hit by lightning, don't get out right away. Give it some time to discharge. Okay, so that is our beginning lecture on the idea of static electricity. Again, static electricity will only flow on the surface of an object, won't flow through anything. Electricity must follow the law of conservation of charge, where total charge of a system remains constant. And remember, there are those three ways to charge an object. Friction, rubbing together, causing electrons to move from one point to another. Conduction, that requires contact, and both things have the same charge after the conduction. And induction, that doesn't require contact, and each object ends up with the opposite charge. See you next time.